So when we talk about separability, we're limiting ourselves to first order equations. I want to address first order equations at the beginning because they're the easiest base case. Once I understand what's going on with them, I can do all the funky stuff and look at how to apply it to higher order differential equations later, but I want to start with first order. So I'm going to make the same remark about linear equations. Let's just look at first order. So we talked about linear equations before. What does it mean for a first order equation be linear? What's it going to look like? This is week one. Pre-Labor Day. Differential equation is linear if, Cody.
If the function f is here,
Which variables?
y,
Oh, hang on a second. This is only first order, so that's really all that matters. It's linear in the variables y and y prime, not necessarily in x or t, whatever our independent variable is. So that means it's going to look like some function of x times y prime plus some other function of x times y equals something else that's only an x. Now I called them A1 and A0 because they go with the first derivative and the non-derivative term. So A1 goes with y to the first derivative and A0 goes with this non-derivative. I think it would be nicer if we had y prime all alone. If I divide this by A1 of x, then my coefficient here, A0 of x over A1 of x, and my right-hand side is now g of x over A1 of x. I'm going to rename those two functions. Let's call this one p of x, and we'll call this one f of x. This is usually called the standard form. Because the highest derivative is isolated. If it's not just first order, but second order, third order, whatever, if I get the highest derivative isolated, that's our standard form. Some linear equations are separable. Depending on P and F, we could get a separable equation. So something like y prime plus 2xy equals 0. That's separable. Because I could write dy dx equals minus 2xy, and then separate to get 1 over y dy equals minus 2x dx. And now I know how to solve that. Even if I just had y prime plus y equals 0. That's separable. There it is separated. Move the y to the other side, then it becomes minus y. Divide out the y, leave the minus behind, and change the dx to the other side. But this equation is linear. It's just barely different than the one above it. And it's not separable. It would be nice if there was some nice trick I could use on the left and right sides of this equation to turn it into something where I could just integrate. I want to consider changing this equation. Not randomly, but deliberately. So I would like you to do me a favor. Let's take that equation, multiply through by e to the x. I promise I'll tell you why in a minute. But I'm going to write this e to the x y prime plus e to the x y equals x e to the x. And now I want to focus on the left side of that equation. Because what I see on the left side are 4 different pieces. I see an e to the x, a y prime. And then I see an e to the x and a y. And I say to myself, hey, what other Calc 1 piece do I remember that when I take a derivative, I get 4 things? And it's 2 things plus 2 things. 2 things plus 2 things. That's what I've got right here. What derivative rule did I use that when I took a derivative, spit out 2 things plus 2 things?
You know, like there's like e to the x, and then there's like plus y, and then you can make it e to the x times y.
That was when I had the plus y in the top, right? But that was just a property of exponentials. And now I'm specifically thinking about derivatives. So I need to go all the way back to Calc 1 where we first started doing derivatives. Long time ago in a galaxy far, far away. Yeah, we were over in admin. What did I do that always spit out 2 things plus 2 things? When I was multiplying 2 things, we had first and second, right? And when I take the derivative of the first times the second, what do? What is the product rule? What is the multiplication rule?
First, second, first.
There's a little more to it than just first, second, second, first. There's a prime somewhere in there. I have to take a derivative. Derivative of the first times the second plus leave the first alone, do the derivative of the second. I just wrote it in a different order from you, Mia, but that's exactly what I want. Wait a second. Let me look back up here. Let me look back up here. The left-hand side of this equation from our differential equation, what's the derivative of e to the x? What's the derivative of y? Leave the first alone, take the derivative of the second. The derivative of e to the x is e to the x. Leave the y alone. This is a product rule. If I take this thing on the left, it's rigged to look like a product rule. Wait a minute, what's my differential equation look like then? Put this over there on the left, put this term up here, and we get my parents are getting on planes, so they're texting people. I apologize. That left-hand derivative is the derivative with respect to x. If I put the dx on the other side, I can integrate. Now, the problem is that in order to do this integral, what do I have to do on the left-hand side? That's after I do the integral. What do I do on the right? I said the wrong thing. What do I do on the right? After I'm done, I'm going to have to divide by e to the x. What do I do first to do that right-hand side? I got to do integration by parts. All right. U dv v du. So logarithmic inverse trig polynomial, LIPET. P comes before E, polynomial before exponential. So U is X. That means the dv is e to the x dx. Means du is just dx. What's the integral of e to the x? E to the x. So v is e to the x. So I get uv minus v du's integral. So that's x e to the x minus e to the x plus c. But on the left, that's e to the x times y. So now, Noah, I can divide out the e to the x. And I get an explicit solution for y. I have a whole one parameter family of answers because I don't know what c is. I didn't get an initial condition. Instead of writing over e to the x, I just wrote e to the minus x. Hey, wait a second. I would like you to take out your graphing device. Use your computer if you want to use graph, or use your calculator, it doesn't matter. Pick 2 or 3 different values for c and draw this. 2 or 3 different non-zero values for c. Let's draw this. before I actually will show you my graphs. What's going to happen as x gets bigger and bigger and bigger? I'm going to go that way. What happens to my y values? Oh, you sure about that?
It's positive up. This.
But it's e to the minus x. Remember, e to the minus x is the same as over e to the x. What happens as x gets bigger and bigger and bigger? This term gets bigger. This term goes to 0. As x gets bigger and bigger and bigger, regardless of the value of c that we pick, this term goes to 0. And that means we have a slant asymptote here. All of our graphs get closer and closer to the line y equals x minus 1. I picked 0.5 and 2 and negative 0.25 for my values of c. But it doesn't matter what value we put here. As x gets larger, this term vanishes. It goes to 0. We've got a stable solution, but it's not an equilibrium solution. Equilibriums are horizontal lines. This is oblique. Okay. Question. Our original equation was y prime plus y equals x. Did this result solve that equation? Or did it only solve the one where we multiply? Let's check. Take this and plug it in for y. Okay, in order to do that, I need y prime. What's y prime? Bingo. So that's y prime. So I have 1 minus c e to the minus x plus y, x minus 1 plus c e to the minus x. What happens when I add those? Because these two pieces cancel and these two pieces cancel. I did solve my original equation by adding in, well, multiplying in this e to the x. So here's the $64,000 question. Where the hell did I get e to the x? Well, it turns out that in every separable, sorry, not separable, linear first order differential equation, there is something I can multiply by that will make this work. Remember, we said that our equation should look like this. Here's the sneaky part. That p of x, I want to use that to build the thing I multiply by. The chain rule, Noah, as you said earlier, when I do the derivative of e to the stuff, that stuff comes down, right? The derivative of e to the stuff is e to the stuff, and then the derivative of the stuff. If I could add an e term, well, multiply an e term, where this piece was the derivative of the stuff, then it would work. So I'm going to create this e to the integral p of x dx. I'm going to call this the integrating factor. Our textbook calls this mu. The calc book, if you still have it, called it I of x. I will routinely screw up and forget which class I'm in and use the wrong one. I'm going to try and remember to use mu as often as possible. Wait a minute. In our differential equation up here, what's p of x? What's p of x in this equation? No, that p of x is just this part. So what's that part on this equation? It's just 1. What's the integral of 1? The integral. And so I would want e to the x, wouldn't I? The integrating factor I get when I use this idea up here is e to the x. I didn't pull it out of thin air. I just didn't tell you where I was getting it from. Hey, I like this idea. Let's see if we can have this work in other places. As long as I can figure out a way to do the integral of p of x, this should work. Now, my first reaction is to say, this is disgusting. It's not separable, because if I move the y term over, the 3x squared goes with it, and then I can't factor and have something with x multiplied with something with y. But this is linear in standard form. I've got a p of x next to that y value. What's my integrating factor for this setup? Exactly. It's e to the integral of p of x with respect to x. So let's take a look at what happens if I multiply each of these 3 pieces by that. I get e to the x cubed y prime plus 3x squared e to the x cubed y equals x squared e to the x cubed. Notice that in each of the pieces, I put the e to the x cubed in a different spot. In the y prime piece, I put it on the left. In the y piece, I put it in the middle, so it would be next to the 3x squared. And on the other side, I put it all the way on the right, so I'd see x squared e to the x cubed. Now notice, first part, derivative of the second. The second's left alone, and this is the derivative of the first part. The left side is now a product rule. This is the magic of my integrating factor. It always causes the left side to become a product rule. Okay, wait a second. If this is a product rule on the left, it's the product rule derivative of what? What thing should go in that set of parentheses? Exactly, the first and the second. Which means if I want to get rid of that prime, I just integrate with respect to x. And here's the best part. You know how to do that integral. At least you did at one point. I'm hoping you still do. U sub, yay! U equals x cubed, du is 3x squared. I don't have a 3, so I get a 1/3. But I'm not done, because that result is the result for e to the x cubed y. I need y. Just divide out the e to the x cubed. Again, as x gets bigger and bigger, what happens to this term here on the end? This piece is going to go to 0, so I will actually have an equilibrium solution in the long run. I should get 1/3 as an asymptote. But it's got all these wiggly bits in it because the e to the minus x cubed, this is going to give me some very unusual looking slope field, which you should take a look at because this picture is interesting in my opinion. Depending on our equation, what we do to set up our integrating factor just relies on knowing p of x. Questions? Opportunity. Let's try one more. Warning, warning, a plot complication is ahead. What makes this part of this problem more complicated?
You already have the left side is product rule.
Is the derivative of x times the quantity x plus 2, I'm sorry, is this the derivative of that? See, that's not what this is, so it isn't already set up. But when I start looking at this to see if it's product rule or not, my first reaction is I can't even do what we were doing in either of the previous parts, because in order to be linear, it needs to look like this. It needs to be in standard form. This isn't in standard form. That x squared is in the wrong place. This looks like what we started with at the very beginning when we had this a1 of x routine, which means what I really need to do is divide by that and get y prime all alone before I do anything else. So the first thing to do is to divide this part out. Now we're in standard form. I can't do the check for product rule or even bring in my integrating factor until I have y prime all alone to start with. Unless we get absolutely lucky, Noah, and you're 100% right. If we notice in advance that the left-hand side is already rigged to be a product rule, then I can go for it. There was too much stuff here and it's not product, unfortunately. So, what's my integrating factor? Sure. What do you, I can, what do you want to, what do you get? Which is the same as 1 plus 2 over x, right? And I got to integrate this to do my integrating factor. Yes? So really, I want the integral of this dx. What's the integral of that dx? Now, you'll notice in my integrating factor, I have been using a plus c. Why not? Because what we're going to do is we're going to take e to that, right? And if I take e to that, I'll get e to the x plus 2 ln x. Then I'll get a plus c, right? But that'll be e to the c. And then I'll just have multiplied an extra number everywhere, right? Might as well cancel the number out. I'm almost always going to assume that when I do my integrating factor, that this c is 0. This is almost the only place in this entire semester where you will be able to just ignore that plus c. So this, I don't like this. I've got an ln inside an e. That's gross. Let's separate it and fix it. I'm going to do a bunch of algebra right here. This is e to the x times e to the 2 ln x. What can I do with that 2? I put it in the log as a power. So it'll be ln of x squared. Squares are always positive. I don't need the absolute value anymore. And then the e and the ln cancel each other out. X squared times e to the x. This is my integrating factor mu. So I get this times y prime plus this times p times y. Oh, wait a minute. The x squared here is going to cancel the x squared on the bottom, isn't it? So I'm going to get x plus 2 e to the x y. And then over here, I'm going to get 1 over x squared times e to the x times this thing. That's e to the x times e to the x. What's e to the x times e to the x? Yeah, but when the x is then squared, what do I do with powers of powers? So I just get e to the 2x. I really, 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 really want to do that on the left-hand side. Sorry, on the right-hand side, because integrating e to the 2x is a lot easier than integrating e to the x squared. But on the right-hand side, this is now product rule, which means this is something prime equals e to the 2x. What goes inside that set of parentheses? Exactly. The integrating factor and the y. It's always the integrating factor and the y. Which means I don't have to worry about integrating any of the ugly stuff. The only thing I have to integrate is e to the 2x. And that's a u sub again. Yay! Okay, what's y equal to? As x gets bigger and bigger and bigger, this term with the c in it goes to 0. But this doesn't. Which means we have, again, a bunch of asymptotic behavior. Stable, not equilibrium, but a stable solution. As we get bigger and bigger and bigger, everything gets closer and closer to the graph of this. But that's not horizontal. That's not even a line. That's some funky looking curve. I have heard in some textbooks that any term that goes to 0 as x goes to infinity, when we do that plus c thing, those are called transient terms. This is the only textbook that ever used that in term that I've ever seen. I probably will never use it again. But that's what this is. This is a transient term here on the end because it goes to 0. limit as x goes to infinity of this piece is 0. Questions?
You're saying the C part is a transient term?
Yes. Again, that's a term I'd only heard in this textbook. I understand why they use it. In the long run, it doesn't matter. Its influence is only temporary when x is small. Although small is a relative term. So its influence is transient. Other questions? I got one for you. What interval is this solution defined on? I haven't mentioned intervals all day today. Makes me twitchy. I need to mention my intervals. Solutions need intervals. Where's this thing effed up? 0. So either it's good on the left side of 0 or the right side of 0. And what's going to tell me? My initial condition. But I can also go back to the original setup. Before I even solved it, I had to divide by 0 to get, divide by x to get my standard form. That gave me x equals 0 on the bottom. That's a singular point, a singularity. We can't divide by 0, so I have to exclude that. Our solutions only exist away from our singular points, either to the left of 0 or the right of 0. Example 4 on page 60 divides by x squared minus 9. I've got two singular values then, -3 and +3. My solution is either only good for x less than 3, x between -3 and 3, or x bigger than 3. Singular points are important, and we will work around the singular points as often as we can. Our discontinuities carry over to our solution curves. So we had a discontinuity here at 0, and when we solved it, it was still not continuous at 0. Almost every linear first order differential equation will end up with a solution with some sort of e to the x in it, e to the minus x, e to the stuff in it. Almost always we will get an exponential somewhere in here. Almost always. And that means if that e has a positive power in our transient term, it won't go to 0 when we go to infinity. It goes 0 the other way. So we would have unstable behavior when the exponent on e is positive, and we would have stable behavior when it's in the denominator or when that exponent is negative. Questions? This looks like our salt tank model. Wasn't that the salt? Oh, wait, there was a salt in, wasn't there? I'm missing a piece. I think this was the homework problem number 6. I'm missing something.
It was 3 down.
Right, so it's 3 minus this, right? Like that? Or was there a 3 on the inside?
Yeah.
Oh, well then, let me look at the answers on our Canvas page. There it is. 6 minus, okay, the number's wrong, let's. dA dt equals 6 minus 2 over 300 plus t, and a of 0 equals 50. That's not separable because of the 6. But it is linear if I put that on the other side, a of t. I need the a. If I put that a term on the other side, dA dt plus 2 over 300 plus t, a of t equals 6. I have a p of t, not p of x, but it's still linear. I now know how to solve this equation. And what's more, if my final result has an e to a negative thing in there, then the amount of salt will converge to a fixed value, our equilibrium solution. Question. Okay, you've already seen models that work this way. We just started with separable because they were easier, and now linear makes my life less requiring to do partial fractions. I hate partial fractions. This is nicer. Let's do it this way. It turns out there are two, remember I said sometimes when we're doing the integrals, we might end up with integrals we don't know how to do. There are two commonly used integrals that are functions of x as an integral. The ERF error function and its complement, the ERF-C, get used a lot in integral defined functions. These show up in prob and stats like there's no freaking tomorrow. Why? Because they satisfy a relationship that looks a whole lot like a probability distribution function. Total area under this curve is 1. Sometimes we will end up with integrals like this. This was actually a sample of an integral I don't know how to solve back in Calc 1. I can show you that the integral from minus infinity to infinity is the square root of pi over 2. Sorry, the integral from 0 to infinity is square root of pi over 2. But that requires Calc 3 techniques. If you see integrals that get written like this, you can rewrite them. On our Canvas page, I found a calculator program to do this valuation and this valuation. So if you want to download this calculator program to your graphing calculator, you need a USB-A calculator cable that connects to this port on your calculator. or the chart report, if you've got the color version, you put the program on here. Then you have to do those calculations by hand. That calculator function also exists in Excel. So we may run into it a couple times. On page 62, they have an example with it. There are also two functions related to sine. There's a function called SI. It's in problem number 47 and 48. I'm not going to use those very often, but if you see them, that's where they're coming. These are Fresnel integrals. We just talked about Fresnel a little bit back in Calc 1, so it was a long time ago. I will see you all on tomorrow. I will remember what day of the week I have you guys eventually. I'll see you all tomorrow. Have a wonderful rest of your day. You too, Noah.